Hello, everyone, and welcome back to PyData Global 2025. Uh, and today's talk, we have When the Meter Maxes Out, Chernobyl Disaster Lessons for Machine Learning Systems and Production. Our speaker will be Idan, and the floor is yours, Idan. Give me a second.
Thank you very much, Enki. Great. So, hi everyone. So when you think about Chernobyl, I guess you probably don't think about recommender system outage or something, but the parallels are annoyingly good. So actually, I knew the Chernobyl disaster when I was young, but when I watched the HBO miniseries back in 2019, I thought this is exactly how ML systems fail. And I'm glad I've waited so long to make this talk since then, because since then I gained so much experience in messing up production systems, of course. So Chernobyl is just a metaphor here. Actually, the real point is the machine learning systems. So no need for any nuclear background or physics or something. I'm myself no nuclear expert. So if I get the details slightly wrong, so forgive me. As the Soviet saying goes, facts are just obstacles to a good report. So let's start. Let me start with one moment that captures the mindset and the failures we will be talking about. So first of all, Chernobyl was a nuclear power plant in what is now Ukraine, and back in the day it was USSR. It supplied power. It was a power plant to the surrounding region, and the day of the disaster itself just began as a routine safety test. They tried to do even a couple of years before, also a couple of times, just a test. But within seconds, the reactor tore open and released massive amounts of radiation into the air, into the night. So that was the main disaster and the following. And the only working dosimeter, which is like this device over here, the radiation, it's a radiation instrument that measures the absorption of radiation. So it's saturated on 3.6 Röntgen per hour. And this number is manageable. It's not good. It's manageable, but actually in practice, it meant nothing. And not good, not great, not terrible is a thing attributed to the supervisor in the control room, um, because that's what it is. So it's not that little, but it's not good. But the reality was that the truth was thousands of times higher. And the reason that the dosimeter showed 3.6 is because it saturated at that number. So it couldn't show any number higher than that, you know. So that's one of the problems. And as consequences of this explosion, so Pripyat is nearby city that was actually built to operate the plant, just continued its life as normal for 46 hours before they been evacuated. Thousands died in the immediate response, and thousands more suffered long-term effects. And this small misleading number, just an example of how catastrophic misreads it can cascade in complex systems. Um, and you can ask yourself, what this number said, and people trusted this instrument, they trusted this number, and it propagated up to the officials over time. Because it just gave a number. It gave any number and they could just rely on it. And if I want to be fair, people, at least the professionals at the control room, I guess they knew the dosimeter is saturating at 3.6 and they knew that the actual radiation is higher than that. But even then, I don't believe they thought that the reactor core had exploded or the number is that high. But actually, the meters, the instrument they had, just couldn't help them. So let's say the first lesson we can talk about is that instrumentation is not a ground truth, it's just a model of the truth. Um, so a bit about me. My name is Idan, Richman Goshen. I'm basically an economist, turned data scientist a few years ago. Love coding since childhood. I'm a board member of an NGO about making cities more community oriented and forming communities inside the city. And I worked also in small companies and large companies. So Chernobyl actually operated almost a decade before the explosion. So it was a functional power plant. And even here in the timeline, you can see that it continued operating years after the explosion, until the year 2000 when it finally shut down. And the mitigation measures to lower the radiation and to contain the radiation near site is was a lot of years, even forward. Um, Today we will talk about the day of the explosion, so a bit before the explosion and a bit after the explosion. We'll focus on that, and we'll go through failures, and each one will be a map to a modern machine learning failure we can talk about. So as I said, basically the whole disaster happened during a safety test. So it was just a routine procedure. They wanted to test if the reactor could keep the turbines, spinning the turbines that make the electricity, if there is a power loss, there's a blackout. So just a test. But let's start with this first failure. We will talk about several things here. The first one is just make it work. You know, it was a lot of operational pressure um, to pass the test. And it was delayed. As I said, it was even, they tried to do the test a couple of years before and they failed and they needed to do it again. They needed to pass the test. There's a lot of pressure from the management. And the test was supposed to be in daytime, and it was delayed because the electrical grid, they said we need full power during the day, so do it during the night. But they didn't really plan to do it during the night. And there's a lot of pressure to make this thing work. So what the analogy for that for us? So let's take an example of a recommender system just built in a hurry. And that recommender system uses multiple user features, and you're on a tight deadline, and you cannot linger on a thorough EDA and feature engineering. You just need to make it work. And we're professionals, so let's say for each feature, we handed nulls or imbalanced data, and the training set a certification to make things not biased. And still, it failed. So what went wrong? There was a bug in the upstream users table, and all the users' features become null. And then it was passed to our model, and our model failed. And just because of the hurry, we didn't account for this scenario, and we just returning errors. So basically, usually management or managers will try to stress us and want the fast delivery. But if product may promise the deadline and marketing already planned the campaign, but our metrics are not validated, we didn't do any safety margins for our model. We didn't do proper testing. We didn't configure any monitoring. So I think we're about to fail. So if you try to learn what are core lessons from that, at least. So first of all, speak up. Management wants something very, very fast. Just say, no, it can't be done. Or you know what, it can be done, but these are the risks, okay? And even if it's done in a hurry, so just don't think everything will work okay and prepare, except for the worst, prepare some fallbacks. And of course, don't deploy on Friday. Our next example is safety override. So the operators, they just disabled the regular emergency systems and safety systems, not because they were unprofessional, just because the test itself that they wanted to pass couldn't work with those safety measures. They were just being triggered, and they had to do something about it. They just couldn't go regularly. So our example here, to go for a minute, is let's say we have a forecasting model for electricity demand, and there's a storm. So during the storm, supply and demand are fluctuating. It's not a regular regime of work, and all our alerts and dashboards, they just go crazy and they start fire up. So we can say, okay, let's ignore. The storm is something abnormal. It will pass. Let's ignore all those alarms and tests, and we'll go on. Even in these special cases, we need to remember that we can predict only part of the abnormal behavior. It could be storm, it could be Black Friday, and we think we know how it should look like, but actually we don't. So things can go wrong in ways we didn't expect. So if you try to draw a lesson from that case, so we can say, okay, special modes need some special tests, or special thresholds or alerts. So we should plan for that. We should see what would we expect, even if it's abnormal, what do we expect to see, and have some hard limits. What is the hard limit that we know that something is off, is very off, and we need to either stop or revert or do something. And if you bypass safety measures and stuff, just document it, communicate it well to the other teams. Don't just assume everything will go fine. Our last example in this, when we talk about the test or before the explosion, is that the reactor core of this power plant was from the type of RBMK. This is the design of the core, and it has an attribute to it. It's called the positive void coefficient, which the problem was that under the test conditions, part of the test conditions was that they were producing less energy than a regular. So under this test condition, there was a feedback loop that was a bit deadly. So part of the reactor, it's creating heat, it creates steam. When you have steam and less water, so it absorbs less absorption of the neutrons, which makes more reactivity, more heat, more steam, and it's spiraling up. And that's basically what happened that eventually caused the explosion. And we'll talk about this feedback loop and use the example of we have a named entity recognition model deployed in shadow mode. And we have latency around 900 milliseconds, not great, but not very, very terrible. So I think usually when we talk about feedback loop, we can talk about popularity bias, maybe in recommender system, or in this case, we can talk about out of distribution predictions because the test is an out of distribution. But I want to talk about something I think is a bit more nuanced. It's about ignoring second order interaction between components of our system. So as I said, we deploy it in shadow mode, not to interfere the regular flow of the application, just to see what is the latency of our model, to inspect the quality and the results of real traffic. But it's an open loop. It's async way, not to block the regular operation. But actually what happened when we go and deploy it to production is that now that 900 millisecond latency, which we thought is okay. It's okay. It's manageable, not good, but manageable. So it frustrates users, and they press refresh, right? So instead of one request, now we have two requests. And this spike of requests creates more timeouts, or the latency goes up a bit more, and they need to wait more, and they do another refresh. So eventually, the system just gets a tsunami of retries, and it crashes altogether. So what we can learn from it. So first of all, our model is not an isolated component. It's not, okay, we're the data science team. I give you a model to the dev team, just work with it. It's not isolated. And we need to think about, as I said, the second order. So what happens when this component, our component, is in production? What happens if there are a number of retries goes up? It's not just, okay, request a model and go back as a response. Also, another thing we can do to mitigate it, in this case at least, not just do shadow mode. Shadow mode is great, but not just shadow mode. After shadow mode, go for canary deployment, which means we can pass like 1%, 10% of the read traffic to our system and start to see how it behaves. It just give us a more realistic view of how it will happen. Okay, next I will talk about the moment of the explosion itself, and also a few more examples of the explosion. The picture you see here is the reactor core building after the explosion. So our first example, and basically what happened is that when the operators in the control room saw that the system, the core is very unstable, they had like this shutdown button and they could press it, and it's supposed to bring down all the, cool down all the reactor. But basically something they didn't know is that under the test conditions, as I said before, when it produces low power, this shutdown button is actually a detonator. It's like detonates this positive void coefficient, which basically caused the explosion. It would exploded either way, but it just made things a lot worse. So what is the analogy to our cases? So let's say we have a company-side estimator, and we deploy it. It replaces a simple heuristic legacy system done by the dev team, and all is fine. It's working 99.9% of the time. And whenever there is an error or something, it goes to the legacy server as a fallback. The backend team sees that their service is almost never used, so they scale it down, let's say from 6 pods to 1 pod in Kubernetes to save cloud costs. Or, in the worst case scenario, they even kill it entirely and there's no fallback. So what went wrong here? Or everything is fine, right? So let's say an upstream missing feature, as we had in the example before, just kills the new model because we're missing feature, model fails, it goes to the fallback. But now the fallback, instead of getting 0.1% of traffic, it gets 100% of the traffic. As I said before, the fallback service is not ready for this kind of traffic, this kind of throughput, so it crashes. So our entire system crashed, and it's a problem. So what we can learn is, first of all, let's not plan just for the happy path. Things can go wrong, and we need to account for all the dependencies in our system. And quite similar to the ones before, it's not just us. It's not just we're the data science team. We have a model. We need to look at our component or our model as part of a system and think about the other components as well. Especially when the other components are in another team, it's cross-team dependency. We need to make sure the assumptions and communications are something that exists. Also, we can do is consider some simple fallback, not rely on the legacy fallback service that will work. Maybe we can take the logic of the previous system and incorporate it into our code, under our machines, and something that, in this case at least, would solve it because our system is built for 100% traffic and not routing it to some legacy service. Just as an idea, or we can just keep paying for the full legacy system warm service for 100% traffic, but it's not optimal. Okay, let's go for a quick test. Now we are back to a 3.6 Röntgen example. So when you see the following, tell me how do you react? You know. So in your table, you see a timestamp feature with the value of 1970 January 1st. So you say, okay, that's a valid date for our users' login time. No, right? This is a Unix time. We know it's like day 0. You see an ID field showing -1. So again, it said something, and we know something is off. There's a problem. And a bit more subtle is we have the probability prediction model that predicts mostly or all the time ones or zeros. So this also should trigger an alarm in our data scientist said, because we know usually those models don't give just like a pretty 1 or pretty 0. We expect something in between. So it's not a total no, but it trigger something in our heads. So I think that's what happened there with the dosimeter that saturated in the 3.6 Roentgens per hour. Let's take an example. We have a fraud detection model, and we have a dashboard. We measure the AUC of that model, and we see in our dashboard over time stable around 0.95. It works okay. Over time, in reality, we're starting to lose money. Theoretically losing. We don't see that loss, but we're losing money because more fraudsters are able to enter the system. How this happened? So basically, we have our prediction model that creates a score, right? And in the doubting process, they used our score and they set a threshold of 0.8. This is a fraudster. This is not. Let's say even the threshold exists in our system. Another system doesn't matter. When we deploy the model, we did a bit of analysis. We find 0.8 is the right threshold. But now all of the we had some data drift or model drift, and all the scores went a bit down. So our AUC measure, again, we see high number because it is still able, the model still is able to differentiate. We can see here in the graph, still able to differentiate fraudsters from non-fraudsters. But all of the scales of the scores went down and our threshold stayed freezed in 0.8. So although the model does a good job separating fraudsters or not, our decision system saying whether it's a fraudster or not is stale. And we basically don't report any frauds. So first of all, a metric is just a single dimensional model of the truth. So basically, if we add more metrics in here, like a number of frauds we prevent, we would see that number go down. If we add only number of frauds, so let's say on weekends when there's less traffic, we would see this number decline and we say, okay, something is wrong. So basically what I'm trying to say is that a single metric is usually just not enough, and we need to look at multiple metrics. And also collect business metrics or something that is beyond our model or beyond just our component, even if it's lagged, even we can get this data only a day or a half day later. Okay, there's not much time left, so I'll skip this one and I'll go for the last one about the evacuation of Pripyat. So after the explosion, radiation was very, very high, but it took about 36 hours just to evacuate the city. And we can ask why this happened. And basically, it's because officials, they wanted to be sure before they do such a costly or something a very dramatic act, just as evacuating a whole city. And I think the lesson here, or what we see is, big failures, a lot of the times they don't begin with a big boom. We can see here, for instance, We can see our dashboard. One of the metrics just goes up every time a bit. And in this case, it's because our data in team keeps throwing new vendors or data into a system. And when I first built the system, it was built, or the assumption was that this is the number, right, of my input data. This is the distribution. It just goes up a bit after a bit. And if I want to relate to that and go and start to do a renovation of the model, we might end up somewhere having a meltdown. So what I'm trying to say is, don't just escalate when you're certain. Even trust your intuition and nurture your intuition, and escalate when you see something looks off, or you see it's going to be a problem. Don't wait for the explosion itself. So if I try to summarize, so it's not sometimes, or a lot of the times, not just a one single mistake or problem. And usually the environments are something that we're familiar with. We're doing everything by the book a lot of the times. But if you don't think of the second order interactions, if you don't think about the fallbacks, if we don't do cross-team communication and all those things, so just a collection of small things that just turns into a disaster. And it touches everything we can see here. So be aware, think of your things, think how it interacts, and build a very robust ML pipelines. So thank you very much. Any questions? Oh, I see one question. Are you using drift detection in production? So, drift, we have a couple of what is this? We have a couple of drift types, but usually it's according to the use case. And yes, for instance, as I showed before, I'm trying to look at the data drift, having multiple measures of what I expect my data distribution to be. And I usually don't do it like an automatic thing, get all the features and calculate averages and to see what averages. I'm thinking about what are the, let's say, root cause or the most important input features I need to keep track on. So if my system is very sensitive to a number of, let's say, entries of names that I'm getting, so I want to see that this number is not changing over time. It might fluctuate a bit, but it's not very, very changing. So this is the one part. Hope that answered the question. Sorry. Okay, thank you very much.